This is the 15th lecture of this course. So, recall that in the last lecture we discussed the following, that given a matrix M by N over F, where F stands for, as I have said in the beginning, that either Q or R or C, given a matrix, we have defined its row space and column space, row space and column space. So, they are respectively the subspaces, the row space is the subspace generated by the rows of the matrix A. So, this is a subspace of so is M by N, so it is a subspace of Fn. The column space is a subspace of Fm. Hence, the spaces are finite dimensional, their dimensions are respectively called row rank, and here it is called column rank. Then in the last lecture we proved that given any matrix, row rank equal to column rank. Hence, we will from now onwards we will not ever use the words row or column. While talking about the rank, we will simply call it the rank of the matrix A. So, if you recall how we have proved this result. So, the crucial observation was the following, that if a matrix A and B, suppose they have the correct order, so that the multiplication makes sense, then the row space of, so any row of AB is actually a linear combination of the rows of B by coefficients from A, right. So, therefore, row space of AB is contained inside the row space of B. Now, you see, so this is what we have seen, row space of AB is a subspace of row space of B, okay, for any matrix A, for any matrix A. Okay. The question whether can I say the opposite. So, we can say conclude the opposite if A is invertible. That is easy to see, because if A is invertible, then B can be written as, so if B can be, so let us write as let us call AB as C. Okay. Well, what first I have to no, I am not talking about the exact converse. Let us have a look at the following. So, if we set ABC equal to AB, then row space of C is contained in the row space of B. Now, if the row space of C is contained in the row space of B, now since so yeah, actually this is converse. So, that shows that row space of B is contained in the row space of AB. Yeah. So, if B is invertible, for any invertible A, that is what we have got is, for any invertible A, for any invertible A, invertible A, yeah. So, actually it is converse. I said wrongly to begin with, row space of AB is same as row space of B, okay. Because in that case we can write B as A inverse times AB. So, therefore, the row space of B is immediately contains the row space of AB. Okay. So, thus if we starting with the matrix B, if we multiply that by an invertible matrix from the left, then the row spaces of the two matrices they do not change. Now, remember, multiplying by an invertible matrix from the left is we have a different name for that, namely that is row reduction, right. So, thus what we have proved is the following proposition: if two matrices of same order same order, well, I do not need to say same order if I just say they are row equivalent. If two matrices are row equivalent, then they have the same row space. Thus, as in particular, ranks are their ranks are same. Okay, that's what we have proved. Because when we say two matrices row equivalent, that means starting from one by applying invertible matrices, we are arriving at the other. So throughout this chain, the row space is never being changed. So the row space to begin with and the row space we are arriving at the end, they must be the same. Okay, that's what we have proved. So remember, we said that if so the row equivalence is a sufficient condition for having same row space. So the natural question is regarding the converse. Does the converse hold? We will answer to that, and we will in fact show an affirmative answer, but in order to get into the answer of that, we first need to observe something which is also quite interesting in its own right. So let us come back to this proposition. So given a matrix A, any matrix which is row equivalent to A will have the same row space. Now we know that given a matrix A, applying a series of elementary row operations, we can arrive at a row echelon matrix, which we already proved to be unique. So given a matrix A, this is unique. So row space of A and row space of A prime both will be same. Now the question is, can I, so since this matrix is of a very special form, so from that can I say something further? So from this simpler matrix, can I draw can I extract some more information about the row space of A? Indeed we can do. So for that, let us observe that how does A prime look like. So A prime might have some 0 rows which you do not care, and let us say you have so if the size is m by n, so this has n columns. So let us assume that we have R, so R less or equal to m, R number of rows are non-zero. Yeah. So therefore, in the row echelon form, we always keep the non-zero rows on the top with proper arranged properly. So what it means is, suppose the first column, the first row, the pivot lies in the kth column, and for the second row, the pivot lies in the k2th column, and then similarly for the rth row, the pivot is contained in the krth column, then one must have k1, k2, kr. Okay. So the row space of A is thus basically the linear combinations of this, basically the linear combination of these vectors, okay, of this row vectors. Now you see, well, here could be something, okay. Now you see that so if you look at the rows of this A prime, well, this is not, it should not become. So if you look at the rows of A prime, you see first of these rows, so you have R number of such rows, okay, and so the row space, one thing is very clear from the description, that the row space of A, which is same as row space of A prime, has dimension less or equal to R, okay, because it is generated by r, it is generated by r vectors. Okay. So, one thing is clear that dimension, so rank of A is less or equal to number of non-zero rows in A prime. So, next, so are these R set of vectors, is that linearly independent? If so, then we will see the rank is exactly R. Okay. That is now very easy to see. Suppose if we denote the R1, R2, RR are the, so Ri is the ith row in A prime. So, each Ri is thus a vector in, can be regarded as a, if you, so this row if you regard it as a tuple, it can be regarded then it is a vector inside Fn. Okay. So, the claim is this Ri, this set Ri I from 1 up to R is linearly independent. Linearly independent. This is our claim. Why? So, let me write it as a claim. That is very easy to see. So, that means alpha I Ri summation I from 1 up to R is 0. From here we have to conclude each alpha is 0. Now, alpha, so when you multiply this vector with alpha I, then you see the first non-zero coordinate. So, in alpha 1, let us in alpha 1 R1, the first non-zero coordinate will be the k1 coordinate, and k1 coordinate will be alpha 1, right. And you see the k1 coordinate of any other rj is 0. So, therefore, so in this tuple the k1th coordinate is nothing but alpha 1. So, the k1 coordinate is alpha 1. Similarly, so once we consider alpha 2 R2, for that the k2th coordinate will be alpha 2, okay, and this is the first non-zero coordinate, and any other from, and for any other j are the k2th coordinate of alpha j rj is 0, because it is a, this is a pivot. Therefore, so k2th coordinate will be alpha 2, similarly krth coordinate will be alpha r, and there will be something which I do not care, but for my according to my assumption this is 0, that forces each alpha I to be 0. Okay. So, that shows the given a matrix A in its row echelon form, the non-zero rows, they actually form a basis of the, they form a basis of the row space of, they form a basis of the row space of form a basis of the row space of the matrix, given matrix A. So, this also tell you a general method for finding the basis of a given subspace. Suppose I am giving you a set and say I am asking you to find a basis of the vector space spanned by this set. So, this serves as a method. So, what you do is you put those vectors as the rows of some of a matrix, then you bring it to its row echelon form. That is how then in the row echelon form whatever you will have, the non-zero rows will be a basis of the linear span of the set we have started with. Okay. Fine. So, thus what we have proved that in the row echelon form. So, let me just write it, let us record it as a theorem. Given a matrix A, given a matrix A, the non-zero rows of A prime, where A prime is the row echelon matrix row equivalent to A, non-zero rows of A prime form a basis of the matrix of the row space or the row space A. Okay. And consequently, the number of non-zero rows, let me use some non-zero rows in A prime is the rank of A, because it is the rank, it is the row rank, and row rank is the rank. Okay. So, this is what we have proved. Now, the question that we want to ask at this point of time is, so what we have seen is, given a matrix whose space is a given a matrix whose row space is a subspace of Fn, whose basis is, I repeat, given a matrix A whose row space, given a matrix A, its row space is a subspace of Fn, and we have found a basis for that by row echelon form, that is a row echelon form. The row space of the row echelon form is the row space of the given matrix A. So, now somewhat we ask the following question, that given a subspace, does there exist? So, look, earlier we have found that does there exist? Does there exist a row echelon matrix whose row space is okay? There is a question that which is very natural to ask at this point of time, because we have seen that row spaces are subspaces, and any row any row space can be regarded as the row space of some row echelon matrix. So, thus all row spaces are the row spaces of row echelon matrices. So, that is what we have earlier we have just seen. Now, the question is in a sense the opposite one, that given a subspace W, can I view it as a row space of some row echelon matrix? If we recall this, then the answer to this question is also very easy. So, what we do is, since W is a subspace of Fn, Fn is finite dimensional. So, W is finite dimensional. So, what we will do is very simple, we will start, since we know that or does there exist a row echelon matrix. Okay, I think let me somewhat given m and positive integer. So, m is also given of order m by n. Of order m by n, yeah. So, this is the question, given any m. So, I want an m by n matrix to have W, a row echelon matrix whose row space is W. So, that is actually easy. So, W is generated by a finite set of elements, okay, and in fact we know that W is generated by W can be generated by a set W can be generated by a set having at most n elements, okay. Now, what we can do is okay, I think we have to do something, otherwise m can, if m goes arbitrary, it will be a problem, because for example, this statement is not correctly formulated, because suppose W has the dimension of W is much more and m is 1, then certainly we cannot have a 1 matrix. So, we should further impose the restriction that given m n and W such that dimension of W less or equal to m. Okay. So, let me again spell out the let me again pronounce the statement once again. Given two natural numbers m and n and the subspace of subspace W of f n, W of f n of having the dimension less or equal to m, then whether there is a matrix of order m by n whose row echelon matrix whose row space is W. So, from my assumption W dimension W less or equal to m, so we have a set, we have a basis, let us say some basis alpha, well W 1 up to W r, where r is less or equal to m, which is a basis of W. Then with that, so then r is certainly less or equal to m. So, if m is bigger, so we include those many zeros, those many zero vectors in that set. Now, we have a set of m vectors, okay, and each W I belonging to f n. Now, what we want to do is very obvious, we will put the W i's. So, for W r plus 1 and onwards, so we equate them to 0. I repeat, so we define W r plus 1 equal to W r plus 2 up to W m, all these are 0. So, now we consider this matrix. So, clearly by construction this matrix has row space W. Now, as we need, since we need to reduce it to a row echelon matrix, we need a row echelon matrix. So, we further reduce this, and reducing that to a row echelon matrix, reducing this matrix to its row echelon form, we exactly meet up our requirement. Okay. So, given a subspace, given, so thus what we have proved it, what we have proved is, given two positive integers m and n and a subspace of f n having dimension at most w, having dimension at most m, there is a row echelon matrix whose row space is equal to the subspace. So, thus we see all the subspaces are nothing but subspaces, so all the subspaces of f n can be regarded as the row spaces of row echelon matrices. Okay. Now, you see this statement says that there is a row echelon matrix whose row space is W. So, the natural question that comes at this point of time is, how many such row echelon matrices are there? So, yeah, so how many such row echelon matrices are there whose solutions, whose row space is W? So, let me write the question. So, if we say, so since we have answered that, we can record it now as a theorem. So, let us call it theorem 1 and let us call it theorem 2. So, the question, let W m n W and W be as in theorem 2, then is the say if we say R, so so the matrix is that this R is nothing but the row echelon form of this this matrix, which has, so yeah, so W1 up to W r, where the basis of the subspace W, then we add 0 vectors, using this we constructed a matrix and then we reduced it to the row echelon form, which was denoted by R. So, the question here is the So, E is the row echelon matrix is a row echelon matrix unique. It is a natural question because already we have proved the existence of at least one. So, let us try to see that this is a unique. So, suppose we have two row echelon matrices, let us say R 1 and R 2, okay. Both of them are row echelon matrices. Such that both have row space W. Both have order and row space W. So, one thing is clear from that is, so if here the number of non-zero rows is smaller and here it is if something r prime, then r must be equal to r prime. Why? Because what is r? R should be the, so since W is the row space of R1, so this number of non-zeros r should be rank of the dimension of W. Similarly, R2 has also row space W1, so r prime should be the dimension of W, therefore r must be equal to r prime. Okay. So, yeah, so this bottom 0 block of both these matrices are same. Now, I want to prove that this block of size r cross n, they are also same. Okay? Good. So, remember that W is nothing but the linear span of, so what we do is, let us use some notation. So, for R1 maybe A1, A2, AR be the rows of R1, let these be the rows of R1, R1, and then similarly B1, B2 is a temporary notation, be the rows of R2. Okay. Now, therefore, W is both linear span of okay. Therefore, W each AI is a linear combination of the BJ's, right. So, what does then what does this give us then? What does that yield us then? So, if we consider the following matrix, let us say whose rows are just, if you, so the matrices are formed just by deleting the 0 rows. So, this matrix is B1, BR, and then similarly this matrix is A1, AR. So, just put them row wise. Suppose we have these two matrices, I think it is better to write somewhere here, this is it will have so the A1 is a linear combination of BI's. So, what we do is we will consider another matrix whose first row will be the scalars, So, let me just write, if A1 is let us say Ci Bi, then we will write C1 up to Cr in the first row of the matrix. So, this is what we can do for any Aj, that gives us a matrix. So, I mean this we have already seen even in the proof of row rank equal to column rank, that given a matrix, we can construct another matrix C such that this is happening. So, I repeat, the ith row of the entries in the ith row of C will be the coefficient of these vectors array the B1 B2 Br arranged properly. So, when we express AI as the linear combination of Bj's. So, I repeat, start AI, write it as a linear combination of Bj's. So, the scalars that they appear associated as the scalars which are associated to B1 B2 Br, we just put them in the correct order as the ith row of C. This we do for any I. Okay. So, therefore, this matrix is fine. Next, so you see both these sets are bases of W. So, we can do the reverse. So, what I mean is I can have R times D, which is okay, that you can have, because A1 and A2 they are also bases, and the scalars will be and the entries in D will be the scalars which appear as the linear which appear in the linear combination of the rows of Bi as the linear rows of Bi as the linear combination of row of A1 to AR. Okay, the usual thing. So, that shows you D, if you apply D here, then what will you get? So, what you will get is, so D times A1 to AR will be B1 B2 Br. Okay. So, you bring everything on the one side, you see that if you bring everything on the one side, DC minus identity is a matrix times this is 0 matrix. Okay. So, it is the order of that R cross N, right. Fine, that is so far so good. See, so far we have just used these two vectors are these two sets of vectors, they have the same span, but we have some further information that each AI has a very particular form, each AI and each Bj, okay, the very particular form. If you will see here, so if the corresponding to the K1, suppose in AI, if suppose for A1, if the K1 column is the pivotal column, that is the pivot 1, then for other vectors there is all the K1 column is 0. Similarly for similarly here as well, because this is also a row echelon form. So, now we are in a very good shape. Why? So, suppose, so since this is the row echelon form, so it will have pivots. Okay. So, let us assume that J1 up to Jk are precisely the columns which contain the pivots, OLJR. Okay. Good. So, what is the J, let us start with J1. What is the J1 row, J1th column? What is the J1th column of the product? Okay. So, for a product, let us say if you have two matrices M and N, the columns of, so if N has the columns N1 up to N k in let us say in K or whatever, you should not confuse that with this K, let us say NL, then the columns of the product should be this. This is all we have already observed and we have been using since the beginning. So, the jth column of the j1th column of the product will be this matrix times the j1th column here in B. Now, you see what is the j1th column, what is the j1th column here. So, this matrix has been obtained by deleting the 0 rows from R2. Okay. So, what is the j1 column here? So, the first row till the j1 position we have all 0 and j1 position has the pivot. So, therefore, everything else below that will be 0. So, this is basically, so the j1 column is 1 on the top and 0 everywhere, but when we consider this we ignore, we deleted the 0 which are towards the bottom, that means be from the R1 plus 1, R1 plus 1 stage and further below the zeros which appear further below. So, basically this is the vector 1 and 0, 0, 0, 0. So, it is a column vector which is column vector. So, the size of the column vector is it is a column vector. Okay. But what is this? Again you should remember that given a matrix, and these are all fundamental observations while working with matrices. So, suppose you have a matrix, let us say I with m I j, and if we multiply that with 1 0 0 0, what will be the result? So, this will be exactly the first column, right, because so if 1 1, if m 2 1, if m n 1, then this will be m 1 1, m 2 1, m n 1. Similarly, if I multiply, so instead of this vector, if I multiply this matrix from the right by the vector which has R1 and at the ith position and 0 elsewhere, then we will get the ith column of this matrix. So, this is nothing but the first column DC minus I. Now, instead of J1, if we ask J2, so what is IJ2? What is the J2th column? So, what is the J2th column of this this matrix? Again, look here, J2 lies somewhere here. So, along the second row up to J2, all the elements are 0. So, once it is 1 here, rest of them are 0. So, once we delete the last r minus m number of rows, what we see is the J2th column is nothing but the same, just one is at the second position and elsewhere 0. So, then it will be the second. Okay. So, thus what we have seen here is the any L column, L where runs from 1 up to n to k, any j L column is the Lth column of. So, any j Lth column of the product is nothing but the Lth position, Lth column of DC minus I. Okay. Now, we know the product is 0. So, thus we see any Lth column is 0, therefore, the matrix has to be 0. So, DC minus I identity is 0. As a consequence, we get DC minus identity is 0. So, from earlier it implies DC equal to identity, and if you remember both D and C are square matrices. Okay. These are all R by R matrices if you remember. So, we need, so here we have A1 to AR, and then we need R columns and similarly R rows. So, each D and C are square matrices of order R. So, DC equal to identity, that shows that both D and C are invertible because already we have proved that having one sided inverse implies that the matrix is invertible. So, therefore, what we have seen is the matrices obtained by deleting the matrices obtained by from R1 and R2, the matrices obtained by deleting the 0 rows m minus r 0 rows. After deleting the rows, the matrices are equivalent in the sense of row equivalence. Okay. Now, what we do now is, so from the row equivalence of this, from the new matrices, I will prove that when I consider this 0 rows altogether, even then they will be row equivalent, and that will be a contradiction because that will not, well, yeah. So, not contradiction because I have not assumed anything contrary yet. So, that will prove that R1 and R2 are row equivalent. Now, from the in the first lecture we proved that, in the first or maybe third lecture, that two row echelon matrix. So, given a matrix which can be equivalent to exactly one row echelon matrix. So, from the uniqueness of row echelon form matrix, the uniqueness of row echelon form, it will be an immediate consequence that R1 equal to R2. I repeat, so what I have obtained is, so far let me repeat, we have obtained that these two matrices A1 up to AR and B1 B to BR, they are row equivalent. Okay. So, what was the matrix here? C. These two matrices are row equivalent. Remember, these matrices are nothing but obtained by deleting the 0 rows which appear at the bottom, the last m minus r 0 rows. Now, what I am going to say that using this row equivalence, because having invertible multiplying by an invertible, that I mean, since C is, we have already proved, right, the C is invertible, so it is a product of elementary matrices, that shows that these two matrices are row equivalent. So, from the row, so thus row equivalence means one is a multiple of the other by an invertible matrix from the left. So, from the equivalence of these two matrices, I will prove the original matrices altogether with the 0 rows will be row equivalent. How to do that? That is also very easy. So, these are a very elementary observations regarding matrices. So, we need a matrix of order m by m, in order to, we need an invertible matrix of order m by m. Okay. In order to prove that R1 is equivalent, row equivalent to R2, but here the matrix C has order R cross R. So, starting from R cross R, how will we consider? So, we will consider the following matrix. So, it is a block matrix. So, the first R rows and R columns, for in the first R cross R block you will have C. Okay. Now, you have m minus R. So, here you put 0, similarly here you put 0, and in the rest, in this last block of size R minus m cross R minus m, you just put the identity matrix. Okay. Right, you just put the identity matrix. Well, let me give you more explanation. So, first we have to show that this why. So, one thing is clear, that the product of these two will be, so if we do that, yeah, B1 BR and then with the entire 0 row. So, this is nothing but R2. Similarly, if we consider the product, what will happen? So, you see here the coefficients are all 0. So, when you multiply, so when you take the combination of the rows of R2 by the coefficients in the first, coefficients appearing in the first row of this matrix, of this block matrix, you will see that it will be just the coefficient of B1 B2 BR with the coefficients, with the entries from entries in the first row of C, the same so therefore, it will be, the first one will be A1, because the coefficients appearing here they will get multiplied with the last r minus m rows, sorry m minus r rows, but since they are 0. So, basically the what is happening with A1. Similarly, goes for A2, and thus till AR you get. So, I think better way of that you visit you deal it you just suppose you have matrices which are divided in the appropriate blocks like this A B C D and A prime B prime C prime D prime, then it is easy to see that, I mean the blocks are divided in such a way that the multiplication makes sense, then it is easy to see that there can be multiplied just regarding the in the usual in the similar law of multiplying 2 by 2 matrix. You can simply forget them as matrices, and you can perform exactly the same rule of multiplying 2 by 2 matrices A prime plus B C prime, that similarly C A prime, so that you can immediately check, plus D C prime, similar for the other 2 blocks. This happen, okay, this happen. So, so and so remember this is just a generic way. So, if some block has size 0, then automatically, so so if some block has size 0, then automatically that block is regarded as absent, okay. So, with this law you can see that the multiplication here is in the following, that C times, so C into this plus this into this. So, basically C into this block is nothing but our A1 to AR, okay. Now, the rest is, if you see here 0 block into this, it will result in 0, and then identity into 0. So, this will be 0. So, this is exactly R1. So, one thing is clear that if I multiply R2 by this matrix, then I will get R1. Now, we are almost done, we have to just show that this is invertible, and that is also very easy to see. So, suppose we have a matrix A and D, both are invertible, and their inverse is A inverse and D inverse. Then we multiply, what will happen? You see, now it is very easy to see. A into A inverse plus 0 0. So, identity, and then similarly, so now here it will be 0 0, and then finally D, so identity of the proper order. So, a block diagonal, so such matrices are called block diagonal matrix. So, along the diagonal you have blocks and 0 elsewhere. So, for block diagonal matrix, suppose A and both are both are invertible, then this, so if A and B both are invertible matrices, may be of different order. Once you put them as in the as a block diagonal matrix in this form, then this bigger matrix also becomes invertible. So, exactly that is why this matrix is invertible, because already you have seen C is invertible, and that shows R1 is equivalent to R2, since both of them are row echelon matrices. So, R1 will be equal to R2. So, that shows that given, so that answers to this question positively. So, therefore, we add that in the theorem 2. What was theorem 2? Theorem 2 was the given M and N. Theorem 2 guarantees the existence. With that, we have proved the uniqueness. Uniqueness. So, I repeat, given M and N positive integers and a subspace of Fn having dimension less or equal to M, then there is a unique row echelon matrix whose row space is W. That is all we have proved so far, and this observation has some immediate corollaries. So, before getting into corollary, let us observe one more thing, that which I think I should have mentioned earlier. So, in fact, something like that we have already observed when we proved that this is a basis. So, when we prove that this non-zero rows at the basis of the row space. So, how does a typical element look like? So, it will be a linear combination of all of them. Okay. So, mentioned this earlier. So, this part is actually a continuation of this. So, if we consider the collection of let us say, well, if I write down the rows here by R1, R2, well, now we should not mix up this Ri's with the row echelon matrices Ri's, that story is gone. So, R1, R2, RR. So, then a typical element will be X1 R1 plus 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 XR, well, we usually denote by alpha. So, alpha R RR, okay, where alpha I F. Okay. Now, in a typical, we have already observed that for a typical element here, in the tuple, the alpha 1 coordinate will be, sorry, the k 1 coordinate will be alpha 1, the k 2 coordinate will be alpha 2, and the kr coordinate will be alpha r. Okay. And what about the other coordinates? Other coordinates you see will be some combinations of these alpha i's, right, the combinations by the elements which we didn't care, and we have put some generic notation for star. Okay. So, that is what we have seen is this actually gives us a concrete description of the elements in that subspace. Well, let me give you an example. That suppose my row echelon matrix is like this. So, how will a typical element look like? X1, X1, 3x1 plus 2x2 and 4x1 plus x2. So, it is a very special kind of description, very explicit description. It shows, so why special? So, in this description, like given any x1 and x2 here, given any x1 and x2, you have a unique element in the row space, unique vector in the row space whose first coordinate is x1 and second coordinate x2. So, that goes here also in generality, that even the so given any alpha n up to alpha r, the vectors, the row space has a unique vector whose kj coordinate is alpha j, where j runs from 1 up to r, and the other coordinates are expressed in terms of these coordinates. So, you can regard it as follows, that these are my free coordinates and the rest of the coordinates can be formed using the values in the rest of the coordinates are the combinations of these free coordinates. So, therefore, it is a very explicit description that shows some of the that there are some coordinates which are totally free, and the rest can be expressed in terms of that, in terms of these free coordinates. So, the reason for saying this is try to see the contrast. So, when we are having a row echelon form, in the solution space what we have is this n minus the rest n minus 1 variables are free. Okay. The rest n minus 1 variables are free, like the coordinates which do not correspond to any kj, they are free, and the kjth coordinates and the coordinates appearing in kj, they can be expressed in terms of this free coordinates. That is in the solution space, but for row space the exactly opposite thing happens, which is very easy to see here. These coordinates are free, and the rest can be expressed as a combination of them, and combinations also come from these scalars. So, okay. Even earlier I mean in case of solution space, once we assign any values to the coordinates which do not correspond to these kj's, from that the value of the kjth coordinate has been formed using the same scalars, the same equation, okay, using the same scalars, right. Similarly, the scales for in the case of row space, those scalars themselves will give the other those scalars will give us the other coordinates than this kj's. Okay. So, I am with a corollary I will be finishing this lecture. So, yeah, as I said, this has numerous consequences. So, what are the consequences? So, consequences are very easy, immediate. So, corollary. So, earlier we have seen if two matrices are row equivalent, then they are, if two matrices are row equivalent. So, well, let me put it in this way, the following are equivalent. The following are equivalent. What are the following? Following for two matrices. A and B, maybe both having the same size. What are the following? They are row equivalent. Okay. There exists an invertible matrix P such that B equal to P A, and the third one is they have same row space. So, now you see this row equivalence has been now converted to the situation of having same row space. So, the equivalence is easy. We define row equivalence in terms of elementary matrices. Then we have earlier proved that a matrix is invertible if and only it is the product of elementary matrices. So, the equivalence of 1 and 2 has been already proved. Now, from 1 to 3 we have proved in the beginning of this lecture. If they are equivalent, they have same row space. Now, we will prove the converse. So, only we need to prove here 3 implies 1, and that is actually easy if they have the same row space. So, we by applying row operations we will arrive at A prime, which is the row echelon form of A. Similarly, we arrive at B prime. So, both A prime and B prime have same row space, hence since A and B have the same row space, therefore, A prime and B prime will have the same row space. Now, A prime and B prime are row echelon matrices. So, from the uniqueness of theorem 2, it will follow that A prime equal to B prime, that shows A is row equivalent to B. Okay. So, thus the row space and row equivalence are now we can see that they are actually interchangeable, that is, or in other words they are actually equivalent. Okay. So, with that I will finish this lecture. Thank you.